Hello, everyone. I'm Adrian Chu. I'm a fourth-year PhD student in the University of Chicago. And before I begin my talk, I'd like to thank the organizer, Hoju, for organizing this wonderful online seminar for us, the geometric analysts. And today, I'd like to introduce to you a Morse theoretic result. So, in Morse theory, we can relate the topology of a manifold with the critical points of a function defined on the manifold. And then we have min-max theory, which is like an infinite dimensional version of the classical Morse theory. So what do I mean by that? So let B3 denotes the unit ball in the Euclidean space, the three-dimensional Euclidean space. And we'll concern the area functional defined on the space of all surfaces in B3. But in this talk in particular, we'll be more interested in the topology of the space of all surfaces that have genus 0 or 1, B3. Okay, so this is like an infinite dimensional space. We will study the topology of this space, and then via min-max theory, we want to obtain some results about the critical points of the area functional defined on this space above, right? And critical points of the area functional, there are free boundary minimal surface in B3. Therefore, we will obtain a free boundary minimal surface in B3 with genus, index, and area control. Okay, so that's the end of the introduction. So let's begin the first part. We begin by talking about the basic philosophy of min-max theory. So this is a rough sketch. Given a manifold M and a function defined on M, a real function, we can relate the topology of M to the critical points of F via min-max theory in the following sense. So let's consider a very simple example. In the finite dimensional case, where M is the torus, and F is the height function of the torus. So that means we measure the height for each point on the torus from the base point. So let's say this is the base level. So at P1, the height is 0. And clearly, this function F has 4 critical points, right? So the idea of min-max theory is the following. We pick a non-trivial loop C in the torus, and then we do somehow like a pull-tight procedure. So we can push the loop C as far down as possible, like this. Now, the final state, so this loop, we cannot pull it tight, we cannot push it down anymore because it is stuck by the topology of the torus, right? And you see, it is stuck at the point P2. So at the highest point of the loop C, it is stuck at the point P2. And that is a critical point of F. So that is what we mean roughly by detecting a critical point via min-max theory. Okay. And as we mentioned, we're going to, in our case, consider an infinite dimensional space. So the infinite dimensional space will be the following. So we call that B3 is the Euclidean unit 3 ball. And we'll denote by E the space of all surfaces in B3 that are smooth and properly embedded, except possibly at finitely many points. And we will do min-max on this space. Okay, so let me make several remarks regarding this space. So first of all, by definition, if we have a smooth embedded surface in B3, we say that it is properly embedded if the boundary of the surface is exactly where the surface intersects the boundary of the ball. Okay, and moreover, the surface meets the boundary of the ball transversely. Okay, and then in this space, we consider surfaces that are smooth and properly embedded, except at finally many points, right? That means there will be a final set such that the complement S take away P is smooth and properly embedded. So these are the these are the surfaces that we consider. So these are the elements of the space E. So we can look at some examples, right? So this is a example of elements in E because it is smooth and properly embedded. This is also one. Okay. This is also an example because although it has singular points, right? There are only finitely many of them, so it is allowed. Similar for this one, it has only one singular point, so it is allowed. And this one is also okay because it touches the boundary of B3 at only one point, so it is only non-properly embedded at only one point, so that is allowed. Okay, so in fact, like ratiously, if you only have like 3 points in B3, then you can take away those 3 points and then you have the empty set. So that will also be an element in E. As for some non-examples, if you take the upper hemisphere of the boundary of B3, okay, you have a whole upper sphere lying on the boundary of B3. That means the first condition is not satisfied. So this element is not in the space we consider. And if you have two intersecting this, that will also not be an example because you have a singular line. So you may wonder, why do we care about surface with finitely many singularities, right? Why do we allow singularities? The reason is the following. We want to consider all surfaces altogether. Because if you do not allow singularities, let's say you have some genus 0 surface and genus 1 surface, they will be completely unrelated. In this, if you do, they will be completely unrelated under, let's say, the smooth topology, right? We want to use the smooth topology because that would be the topology that allows us to do min-max, the Simon-Smith min-max theory later. So the genus 0 and genus 1 surfaces, they're completely unrelated. But by allowing surfaces with finitely many points, you can do a neck pinch process so that you have some genus 1 surface deforming to become a genus 0 surface. So let me be more precise. What do I mean by that? So let us define on E a topology first, because otherwise it's not a space. So what is the topology we consider? It is like the smooth. It's basically the smooth topology, except around those points of singularities. So if you have a surface S that is an element in E, such that S take away as finite set of point P is smooth and properly embedded, then the topology on E is given by graphical C infinity to convergence away from the singular set P. In other words, if you have a sequence of surface, then we say that the sequence of surface converge to S. So Si converge to S if and only if for any open set compactly supported away from P, the convergence is smooth. So for example, you have a genus 1 surface, you can neck pinch it to be so that it becomes a genus 0 surface. So this is actually a continuous path in E. So you see, if we did not allow a surface of we find a number of singularity, this process would not be well defined, right? And similarly, this in the second example, you can have like a one topological disk being broken apart to two. So this is also a continuous path in E. So now we consider the area functional defined on E, right? And the goal is to relate the topology of E to some critical points of the area. So the area functional is just like we take a surface and then we compute the areas. That's the area functional. And just remark, the critical points of the area functional are free boundary minimal surfaces in B3, so in the unit ball. In other words, there are surfaces with zero mean curvature, and they meet the boundary of B3 orthogonally. So let me now explain the first part. So we have two parts, right? So the topology part and then the part about the free boundary minimal surface. So let's talk about the first part. The first part, we have a theorem that helps us to understand the topology of E. So it describes some non-trivial topology of E. So let us denote by E sub G the set of all smooth G surfaces, okay, in B3. And then E superscript A be the set of all elements with area less than A. Okay, so although some elements in E would not be smooth, but we can still talk about the area because there's only finitely many singularities. Okay, and then the first result is that the first to the sixth cohomology groups in CD coefficients of this space are non-trivial. So what is this space? This space, so if you look at the first component, it is the closure of the space of all surface with G0 and G1. So by taking closure, we allowed some surface to have singularities. So the space that this union space become connected. Okay, if we do not take the union, it is disconnected. And then furthermore, we look at surfaces with area at most 2 pi. Okay, sorry, not at most, but less than 2 pi. Okay, so this bound 2 pi will be important for us to rule out multiplicity when we do max theory. So this is a space of all surfaces, like roughly speaking, a space of all surfaces with G0, 1 and area less than 2 pi. And then the first theorem say that like the topology of this space is not trivial. The first to the sixth cohomology groups are not trivial. So in fact, we will prove a slightly stronger theorem, which says that there's a element in the first cohomology group so that it's 6 power. That means you cut this out a 6th time, and that is non-trivial, non-zero. Okay, so I guess like one may think about, okay, so we have this Hescher's resolution of the Smell conjecture. So one equivalent form of the Smell conjecture says that the space of all smoothly embedded two-sphere in the three-sphere, it can be deformation retracts to a subspace. So the subspace of great two spheres or equatorial two sphere, that means. And that is the finite dimensional space, right? The space of all equatorial two sphere in the three sphere is just an RP3. It's like parameterized by the axis orthogonal to any particular two spheres. So an RP3, so it has 3 non-trivial comoduring, the first, the second, and the third one, right? Yes, so this is like the space of all genus 0 surfaces, right? And then the theorem A here is like, oh, if you want to have more non-trivial cohomology groups, you can consider surface of high genus like genus 0 and genus 1. So this is the idea. Okay, so moreover, one can think about the following. Marcus and Navis, they proved the Wilmot conjecture, and in fact, together with a result by Nurser, we know that the 7th width of the free sphere, of the round free sphere, is 2 pi squared. So this in particular implies that like the space of all flat 2 cycles in the free sphere with area less than or equal to 2 pi squared has non-trivial first to the 7 cohomology groups. So after we have this theorem A, so we have some topological information about the space, and then we can do min-max theory using some phi. So what is phi? Phi would be some non-trivial family in E. So it would be something like a skeleton, a 6 skeleton in the space here, in the space, this space. So phi is something like a 6 skeleton, and then we do a pull-tight procedure. We push phi as far down as possible, like in this case, right? Like in this case, so we push it down as much as possible. And then min-max theory will tell us this phi will get stuck at the critical points. So therefore, we obtain a minimal surface. So this is the idea of min-max theory. And then we have theorem B, which describes this minimal surface. The result is that there exists a free boundary minimal surface such that the genus is 0 or 1. The Morse index of the minimal surface is 4 or 5, and the area is between pi and 2 pi. And moreover, this surface is not the equatorial disk or the critical catenoid. So you know, Morse index is difficult to compute actually. So we only know the Morse index of 2 free boundary minimal surfaces in B3. It's the critical catenoid and the disk. So they have index 1 and 4 respectively. So theorem B tells that there's still a low index minimal surface in B. So this concludes the end of the first part. And then in the second part, we are going to, so in the following, I'm going to sketch the proof of theorem A. So this is the theorem A. And in part 2, so there are three parts, sorry. In the second part, we will reduce part A to another theorem, part A prime, okay? And I'll show you how we can deduce theorem A using A prime. And in the third part, we prove theorem A prime, sketch the proof of theorem A prime. Okay, what is theorem A prime? And how do we deduce theorem A from it? Theorem A prime is it concerns the phi that sorry, it's not phi, right? I mispronounced it. It's psi. This one is psi. So there is this sweep up psi. This is a 6 sweep up, and I'm going to introduce what the word 6 sweep up means. Okay. So the family psi is so it's a map from X into this space we concern, right? In fact, X will be 6-dimensional. So psi is like a 6-parameter family of surfaces in B. So because this is like the space of all surfaces in B, right? So we have a 6-parameter family of surfaces in B. And so this is psi. And then we embed this space we consider into the space of all flat cycle, flat 2 cycles with the flat topology. Because the surfaces we consider in this space, they're smooth, except finally many points, right? So therefore, and they have finite area. because we bound the upper bounded area by 2 pi. Therefore, they will be a rectifiable occurrence, and in fact, there are 2 cycles in B3, and then we equip this space with the flat topology. Okay, and because the smooth topology we use is stronger than the flat topology, it's much stronger. Therefore, this inclusion map I is continuous. Okay, and psi, of course, we assume it is continuous. And then we have the Armgren isomorphism, which says that, which tells us about the topology of this space. So it says the cohomology ring of this space in C2 coefficients is nothing more than the polynomial ring with C2 coefficients. Okay. So basically, the kth cohomology group of this space will be given by lambda to the kth power. So this is what Armgren isomorphism says. Now, the term 6 sweep-out means that this condition is true regarding psi. So if you pull back lambda 6, okay, so lambda 6 is something in the cohomology of this space, right? So we pull it back to x. If the pullback is non-zero, then we call psi as a 6 sweep-out. Okay, so this is the definition of a 6 sweep-out. And we will later show how do we construct this psi exactly. But for now, let's assume this psi exists, okay? And then we want to show theorem A using this psi, right? This is our goal. Okay, so now if psi is a non-trivial, if psi is a 6 sweep-out, then clearly this equality holds. And as a result, this term will be non-zero, right? So this term is non-zero. That means there's something to the 6th power is non-trivial, and this will lie in the 6th cohomology group of the space we concern, right? Therefore, we conclude we've proven theorem A. Okay, the first to the 6th cohomology group have to be non-trivial.